In the previous video, we looked at how a simple electrochemical cell worked by utilising the electron transfer that takes place in a redox reaction. All cells like this are made up of two so-called half cells. In our example, the half cell making up the negative electrode that is supplying the electrons can be described by this half equation. The other half cell that makes up the positive electrode can be described by the following half equation. If we replace the copper half cell with another type of half cell, for example one that involves magnesium metal in contact with 1 moles per decimeter cubed magnesium sulfate solution, when we do this, the electrons travel in the opposite direction. That is, they travel from the magnesium side to the zinc side. In this cell, the Zn2+ ions are accepting 2 electrons from the zinc metal and being converted to the zinc metal. The magnesium metal is releasing 2 electrons and forming the Mg2+ ion, which then enters the solution. This is happening because magnesium is more readily oxidized than zinc. Or we could say magnesium is a stronger reducing agent because it is able to reduce the Zn2+ to zinc metal. The overall ionic equation is therefore as follows. So far then, we have learnt that you can make a half cell by having a metal in contact with a solution of its ions. 2 dissimilar half cells can be joined together to make a cell. Whether oxidation or reduction occurs in the half cell depends on the species it is being paired with. Oxidation, that is, release of electrons, will occur in the cell in which the species is more readily oxidized, and this will form the negative terminal of the cell. So, are we able to predict which way the electrons will flow when we pair together any 2 half cells? And are we able to predict the force by which electrons are pushed around, the so-called overall cell potential, which is measured in volts using a voltmeter connected to the circuit? The answer to both these questions is yes, sort of. We will now learn how it is possible to make these predictions and learn about the limitations of such predictions. The way we can rank the relative ease by which metal ions are reduced, that is, gain electrons, is by measuring the overall cell potential when a particular half cell is measured against a standard half cell. The standard half cell we use is the standard hydrogen half cell, which involves this redox system. Because hydrogen is a gas, we cannot use it to make an electrode from in the same way we can for half cells that involve pure metals. We therefore use a platinum electrode and we bubble hydrogen gas alongside this electrode, and the electron exchange takes place on the surface of the platinum. Platinum is suitable since it is an unreactive metal. For the standard hydrogen half cell, we standardize on 1 atmosphere of pressure for the hydrogen gas and a solution of 1 mole per decimeter cubed hydrochloric acid to provide the H+ ions. We can then connect other half cells to this and measure the overall cell potential using a voltmeter. The cell potential observed is known as the standard electrode potential for the species being studied. Which way the electrons flow depends on how readily the reduction reaction occurs relative to the reduction of the H+ ions. For example, if we connected the Cu2 plus Cu half cell to the standard hydrogen half cell, copper would be reduced, so we would have this half equation on this side, and hydrogen will be oxidized, and the electrons would flow from the hydrogen half cell to the copper, and the cell potential would be plus 0.34 volt at a temperature of 25 degrees Celsius. On the other hand, if we connected the Zn2 plus Zn half cell, the Zn2 ion would be less readily reduced than the hydrogen ion, so electrons would flow in the opposite direction, from the Zn2 plus Zn half cell to the H plus H2 half cell. The cell potential, because the electrons are travelling in the opposite direction, is assigned a negative sign, and its value would be minus 0.76 volt. A series of various half cells placed in order of increasing standard electrode potentials is called the electrochemical series. species that are most readily reduced, that is, the better oxidizing agents, have more positive standard electrode potentials, whereas those species that are more readily oxidized, that is, are the better reducing agents, have more negative standard electrode potentials. By convention, the half equations describing the redox reaction in the electrochemical series are written in the reduction direction, as opposed to the oxidation direction. Standard electrode potentials used to be called standard reduction potentials, and this in some ways is a more helpful term, as the values indicate how readily the reduction reaction takes place. The more positive the standard electrode potential, the more readily the reduction takes place. You will notice some non-metals in the series, and some species that do not involve the oxidation of pure metal, like for example the reduction of Fe3+ to Fe2+. In these cases, like with the hydrogen half cell, a platinum electrode is used as a surface for the electron exchange to take place. If we notice, the standard electrode potential for the reduction of H+ is 0, since if we connected two standard hydrogen half cells, there would obviously be no electron flow. We now know how standard electrode potentials are measured, and we will now learn how we can predict which way the electrons will flow when connecting two half cells. We will stick with our cell that involves Cu2+/Cu and Zn2+/Zn half cells. Let's look at the standard electrode potentials for both of these. We see the Cu2+/Cu half cell has a standard electrode potential of plus 0.34 volt, and the Zn2+Zn half cell has a standard electrode potential of negative 0.76 volt. Oxidation, that is loss of electrons, will occur at the half cell with the more negative standard electrode potential. Or in the case where both half cells are positive, oxidation will occur at the half cell with the least positive standard electrode potential. This will form the negative terminal of the cell, and consequently the half equation that occurs is the oxidation one. Reduction occurs at the other electrode, and we can obtain the overall ionic equation by adding the half equations in the normal way. We can predict the electron flow, that is, from the negative terminal, where electrons are released, to the positive terminal, and we can predict which species will be reduced and which oxidized. To predict the cell potential from the standard electrode potentials, we just take the difference between the two standard electrode potential values. For our copper zinc cell, this is 1.10 volts. As a formulae, it can be worked out as the standard cell potential equals the standard electrode potential of the half cell that forms the positive electrode, subtract the standard electrode potential of the half cell that forms the negative electrode. We can use standard electrode potentials to predict the feasibility of redox reactions. Just a look at where the different species are in the electrochemical series will show that a species with a more positive standard electrode potential will oxidize a species with a less positive standard electrode potential. Copper will oxidize zinc, for example, but will not oxidize Fe2+ to Fe3+. Such predictions do have limitations, however, because a given reaction may appear feasible, but the activation energy for the reaction is so high the reaction may not occur, or the rate of reaction may be extremely slow. As a rule of thumb, if the calculated cell potential is less than plus 0.40 volt, it is unlikely the reaction will occur. Also, we must remember that the standard electrode potentials are measured under standard set of conditions. The solutions of each species of the same element are 1 mole per decimeter cubed, or equimolar, and the temperature is 25 degrees C, and any deviations from these conditions could affect the validity of any predictions. We can think of each half cell as a pair of species in equilibrium. In the case of the zinc half cell, copper, being a stronger oxidizing agent, is able to remove electrons from the left-hand side and therefore push the equilibrium to the left. On the copper side, because zinc is a stronger reducing agent, it is able to add electrons to the left of this half equation and therefore push the equilibrium to the right.